Hi all. In the last classes we have discussed how to represent a linear transformation from V to say linear transformation T from V to W using a matrix, or what is the matrix representation of that. I'll remind you that again. This V is the vector space and W is two binary dimensional vector spaces are there, and both are defined on a common field F, and I assumed V is the vector space of dimension n and W is the vector space of dimension m. So we can represent this T as a matrix. For that we consider two ordered bases. Say B is the ordered basis of V, consisting of the vectors alpha 1, alpha 2, etc. alpha n, and B prime is the ordered basis corresponding to the vector space W's, and it consists of vectors beta 1, beta 2, etc. beta m. So these are the two bases. Then how to represent T with respect to this relative to the bases B and B prime, that is a notation for that matrix. I'll write that matrix as A, the consisting of the entries Aij, and this Aij is defined using this equation: T alpha j is equal to summation I equal to 1 to m Aij beta I. Okay, so this is A11 beta 1, A21 beta 2, and so on, and this is true for j is equal to 1 2 3 etc. n. So this defines the entries of that matrix A. So this is the matrix representation. If in the case if B is equal to B prime, if we are considering a linear operator from the linear operator T from V to V, then you can take this B is same as B prime. Then in that case we represent that we use the notation for that matrix as matrix of T relative to the basis B itself. Okay, you need not worry about the this B prime. Okay, now we have two examples here. This is example 14. In example 14 we consider F2. If F is a field, then consider the vector space V as F2. So this is a two-dimensional vector space over F. Then T is the linear transformation from F2 to F2 defined by x1 x2 is mapped to x1 comma 0. Now how will you find the matrix of T relative to some basis? Okay, if you take a standard basis B consisting of vectors epsilon 1 and epsilon 2. What is epsilon 1? Epsilon 1 is epsilon I is defined as or I'll write this as epsilon 1. Epsilon 1 is defined as this 1 equal to 1 comma 0. Then this is our 1 comma 0. This is our epsilon 1. I'll write this as epsilon 1 is equal to 1 comma 0 and epsilon 2 is equal to 0 comma 2, 0 comma 1, sorry, 0 comma 1. So these are the basis vectors. Then what is the matrix of T? That is obtained by T of so in this case we have B same as B prime. So we choose an element T epsilon 1 from B, then take the image. What is T of epsilon 1? That is T of 1 0. What is T of 1 0? By definition that is 1 0 itself. So this 1 0 can be written as 1 times 1 0 or 1 times epsilon 1 plus 0 times epsilon 2. Okay, so this will give the first column of the matrix of T relative to the basis P. Okay, so this the first column of that matrix can be written as 1 comma 0. So that is this is our A11 and this is our A21. Okay. Similarly, you write T of epsilon 2, that is T of 0 1. By definition that is 0 0 because x1 is 0 here. So the x1 comma 0 is the image. So that will be written as, that can be written as 0 times epsilon1 plus 0 times epsilon2, and this is our a12 and this is our a22. Okay, in that case the column, the second column can be written as 0 0. So this is that matrix. Okay, so this is the matrix of T relative to the basis B. That is what we have discussed in example 14. Now we discuss example 15. In example 15 we have, this is our example 15. In this we consider V is the vector space of all polynomials over R. So we represent that as R of X. So this is the polynomial of set of all polynomials of over R. But if you consider this, then this will not be a finite dimensional vector space. Okay, so we consider V be the space of all polynomial function from R into R of the form C0 plus C1x plus C2x x square plus C3x cube. So that is set of all polynomials of degree at most 3 along with 0. Okay, so this is our from R of X we choose a polynomial whose degree is at most 3 along with 0. So this is our vector space. We write V as set of all polynomials of the form C0 plus C1x plus C2x square plus C3x cube, where the Ci comes from R. Okay, so this is our vector space. Now we define, so this is an arbitrary element. We represent that arbitrary element f of x C0 plus C1x plus C2x square plus C3x cube, and we define a linear operator D. D is the differential operator. So D of f of x is nothing but f dash x. In this case, this f dash x is C0 will be 0 and the first term will be C1 and 2 C2x plus 3 C3x cube. This is the differential operator or differentiation operator of on the vector space of all polynomials of degree at most 3. Now we need to find the matrix of D. Matrix of D with respect to the basis B. What is B? B consists of the polynomials 1 x, x square and x cube. Okay, we write fi of x equal to x, I write fj as same in the example, fj of x equal to xj minus 1. Okay, so then what is f1? This j varies from 1 to 3, okay, and 4. So we have 4 polynomials. What is f1? F1 is x raised to 1 minus 1, that is x raised to 0. F2 is, the second one is x raised to 2 minus 1, that is x. Next is x raised to 3 minus 1, that is x square, and last one is x raised to 3 minus 1, 4 minus 1, that is x cube. Then how will you find the matrix of D relative to the basis B? For that we consider the images of these f1, f2, f3, f4. So what is D of f1? D of f1 is D of, that is the derivative of f1 of x is nothing but this one. Okay, so that is equal to 0. Similarly, what is D of f2? Okay, the 0 can be written as 0 times 1 plus 0 times x plus 0 times x square plus 0 times x cube. Okay, so this will constitute the first column of the matrix of D. Okay, so I write the matrix of D here. This is the matrix of D relative to the basis B. So what is the first column of this? First column can be written as 0 0 0 0 using these coefficients. And what is D of f2? D of f2 is D of x, that is derivative of x. Derivative of x is 1, that can be written as 0 times 1 plus 1 times 1 plus, so that is not 0 times 1, that is 1 times 1 plus 0 times x plus 0 times x square plus 0 times x cube. So from these you can get the next column, that is the first entry is 1 and the second entry is 0, third is 0, fourth is 0. Okay. Now you write D of f3. D of f3 is equal to D of x square that is equal to, what is the derivative of x square? That is the linear operator d. So you write this is d of x square is 2x. Then this can be written as 0 times 1 plus 2 times x plus 0 times x square plus 0 times x cube. So these coefficients constitute the third column of the matrix of D. So that is 0, 2, 0, 0. Then from D of F4 we can get the last column, that is D of x cube. D of x cube means derivative of x cube, that is 3x square, that is equal to 0 times 1 plus 0 times x plus 3 times x square and 0 times x cube. Okay, so this will give the last column of that matrix. Okay, because this is our a11 and this coefficient is a21 and this is a31 and this is a41. So that is the first column, and similarly this will give the second column and third column and fourth column. So we write this is 0, 0, 3, 0. So this is the matrix of D relative to the basis B. Okay, so this is the 15th example. So these are the examples for the matrix representation of different linear transformations on a vector space. Next we will discuss the most interesting result of chapter 3. In this chapter we will discuss, in this section we will discuss the matrix of matrix representation of the composition of two linear transformations. Okay, let T be a linear transformation from this is our T from the vector space V to W, and U is another linear transformation from W to Z. Z is another vector space, and we have assumed V is a vector space of dimension n, and W is a vector space of dimension m, and Z is a vector space of dimension p. Okay, now if we set three bases, B consisting of alpha 1, alpha 2, etc., alpha n is a basis for V, and ordered basis for V, and B prime is equal to is a set of all vectors beta 1, etc., beta m. So this is the basis vectors for W, and we write B double prime consisting of the vectors gamma 1, gamma 2, etc. Gamma p is the basis vectors for set of all basis vectors for Z. Then we can represent the matrix of T using or relative to the basis B and B prime, and we denote that as A, and you can represent the matrix of U relative to the basis B prime and B double prime. Okay, and we represent that as B. Okay, then the ijth entry of this matrix is given by the formula T alpha j is equal to summation k is equal to 1 to m a k j beta k for j is equal to 1 to 3 etc. n. Similarly, the ijth entry of B is obtained by u of this beta k, that is u of beta k is equal to summation I is equal to 1 to p. This is beta bi p bi k, and this is our gamma I. This k varies over k is equal to 1, k varies from 1 to m. So these are the definition of A and B. Then using this A and B, we will find the matrix of the composition. Okay, that is UT. The linear transformation UT is from the vector space V, the domain of T, to the codomain of U. Okay, so that is Z. Then you can fix by fixing these two B and B double prime, you can find the matrix of UT relative to the basis ut relative to the basis b and b prime. Okay, and if I call that b double prime, if I call that matrix as C or Cij is the arbitrary element of that ijth element of that matrix, then this is obtained by from this you can say that this is the this akj is the jth column of the matrix A. Okay, so in order to get the jth column of the matrix C, we start with u t of alpha j, because this B consisting of the vectors alpha 1, alpha 2, etc. alpha n. So jth column is obtained by evaluating this ut of alpha j. What is ut of alpha j? Ut of alpha j is u of t of alpha j, but t of alpha j can be replaced from this equation. From this you can write what is t of alpha j, that is equal to u of summation k equal to 1 to m a k j beta k. So that is equal to, since the u is linear transformation, then you can distribute this u, that will give summation k equal to 1 to m a k j u of beta k, but u of beta k is this. Okay, so then you can write that is equal to summation k equal to 1 to m a k j, and this u of beta k can be replaced from this equation. That is again summation, that is summation over I from 1 to p, this b I k gamma I. Okay, so this can be written as, since this akj is independent of I, then you can write that is summation k equal to 1 to m and summation this I equal to 1 to p. This can be, this akj can be taken inside, then I will write this b I k and akj times gamma I. Okay, now you can interchange this summation, since it contains only finitely many elements, then this interchange of summation is nothing but the order of the summation. Okay, so we'll write the summation I over 1 I varies from 1 to p first, then we write the summation k varies from 1 to m, then a b I, this b I k first, write b I k and a k j times this gamma I. Since this I is independent of k, then you can take this gamma I out from the first inner summation, then this will give this one. Okay, now we have started with ut of alpha j. Okay, then ut of alpha j is equal to this times gamma I. Okay, that means this will give the, or this constitute the jth column of that matrix, jth column of C. Okay, so what is the jth column of C? So the expansion of the inner sum, this summation varies over k equal to 1 to m will give the jth column for each I is equal to 1 to 3 etc. Okay, then just observe this summation k equal to 1 to m b I k a k j. When k equal to 1, this will be b I1 a1 j plus bi2 a2j. Okay, so the sum is nothing but b1k b2k etc bmk times this a1 sorry, this is our this in sum is bi1 bi2 etc bim. So that is the entries when k varies from 1 to m, and for the next entries we have a1j a2j etc amj. So this product is given in this bracket. Okay, so this bracket is nothing but the product of ith row with the jth column of A, ith row of B with the jth column of A. Okay, so that is the ijth entry of, so this will give the ijth entry of the product BA, the product of the matrix B and A. Okay, so this is the ijth entry. So when you fix for corresponding to each I, you will get the ijth entry. Okay, as this bracket. So this ij, so this constitute the jth column of the matrix of ut. So the matrix of ut relative to the basis, b double prime will give the jth column of this matrix is coming from this bracket, and the ith entry of that will give the ijth entry of the product I, product B times A. Okay, this shows that the matrix of ut, that is defined to be that is denoted by C here. Then C is nothing but ijth entry of C is given by ijth entry of the product BA. Okay, so this shows that our matrix of ut relative to the basis, this ut relative to the basis B and B double prime is nothing but the matrix BA. Okay, so if the matrix of U is B and the matrix of T is A, then the matrix of UT, the composition is nothing but the product of matrix. Okay, so this product is defined as the usual product what we have learned from +2 classes onwards. Okay, so this is one of the reasons why we define the product of two matrices in that manner. Okay, usually you can define the matrix, you can multiply two matrices A, B, C, D, X, Y, Z, W in the corresponding elements. Okay, A, X, B, Y, C, Z, D, W. This type of product is also there, but we are not using this product from +2 onwards. Okay, so the usual product is in some other way. We will multiply A with X, then B with Z and all. So if you consider that product, then that product coincides with, or that product will enable us to define the matrix of composition of two linear transformation as the matrix product. Okay, when you define this product, that doesn't work here. Okay, so this is why we defined the product of two matrices as in some complicated manner. Okay, so this is the easiest product, but this cannot be used in this situation. So the product, when you defined in the +2 classes onwards, is the product of two matrices, usual product of matrix, that will work here, because the matrix of the composition of two linear transformation is defined as the product of two matrix. The product is defined in the usual way. Okay, so that's why we call this is an interesting theorem. These all things can be combined in theorem 13. Let V, W and Z be finite dimensional vector space over the field F. Let T be the linear transformation from V into W, and U is a linear transformation from W into Z. If B, B prime and B double prime are ordered bases for the vector spaces V, W and Z respectively, if A is the matrix of T and that is relative to the basis B and B prime, and B is the matrix of U relative to the corresponding basis, then the product of the matrix of the composition is nothing but the product. Okay, so this is the proof for or this is the proof of theorem 13.